Thank you, Guillermo, for introducing me and for having me here to speak, and for everybody to stick around at this late time of the day here to listen to this. Okay, I want to talk about q-polymatroids and independent spaces. This is based on joint work with Benjamin Jany, who's my grad student. So let's get right into it. Here, time is short. So first of all, what are q-polymatroids and q-matroids? We've heard about q-matroids from Relinde's talk. Q-polymatroids are a slight generalization, yet that slight generalization really makes a big difference. So let me remind you what q-matroids are, and I'm going to introduce right away q-polymatroids. So we start with a ground space, Fq to the n, a vector space over a finite field. And then we look at the lattice of all subspaces of that. Okay, so, and then a q-polymatroid on Fq to the n is a pair consisting of the ground space and a rank function, rho, which takes values from the lattice, or that's our domain, and spits out non-negative rational numbers. That's a q-polymatroid. Non-negative rational numbers. Sorry, I'm not done yet. The rank function has to satisfy certain properties, a list of properties. The rank is always upper bounded by the dimension. The rank function is increasing in the sense of property R2 there, and property R3, a submodularity condition. So this is exactly what we also saw in Relinde's talk. So, and the only difference to a q-matroid is that we have here non-negative rational values for the rank function. In a q-matroid, the rank function takes natural numbers or non-negative integers as rank values. So that is the difference. Q-polymatroid, rational values as ranks, q-matroid, integer values, non-negative in either case. So for q-polymatroid, since we have rational numbers as rank values, we can talk about the denominator of a polymatroid. That is just any common denominator of all the rank values. There are finitely many rank values. This lattice is a finite lattice. So any denominator of these finitely many common denominator is called a denominator of the polymatroid. I need that notion later. So there are many denominators. We can focus on the least denominator if we want to, but there is no need to do so. So q-matroids have been around for a while actually, but I think the go-to paper when the topic took off is the one by Relinde and Pellikaan from 2018. And so why the interest in q-polymatroids? Okay, because these objects are induced by rank metric codes. I don't want to show how that works precisely because that's really not relevant for this talk. We don't need that, but it's just good to know that's why the interest is there recently. So, and as Relinde also pointed out, the following, Fq to the m-linear rank metric codes of length n, so living in that space, give rise to q-matroids on this ground space, Fq to the n, that same n, but arbitrary, or well, rather Fq-linear rank metric codes, so matrix rank metric codes if you want, give rise to q-polymatroids on the same ground space, and m is a denominator. Not necessarily the least denominator, but it is one. And of course, we could swap the role of n and m, but let's focus on this one here. So rank metric codes give rise to q-matroids if they are highly linear over an extension field, and in general, if they are just linear rank metric codes too, they give rise to q-polymatroids. So that's the reason why they show up now in the coding literature as well. It's not surprising, many invariants of the code can be recovered from the q-polymatroid. Several papers exist about that. At this point, I want to mention, and also something that Relinde mentioned already, concerning the first statement here, it is not the case, not every q-matroid is induced by an Fq to the m-linear rank metric. We can find examples of that. Okay, so this is kind of the Q analog of non-representability of classical matroids, if you want. So, but it leaves open the question whether every q-matroid is induced by an Fq-linear rank metric code, just a matrix rank metric code. It could be, in some cases, they give even rise to q-matroids, so denominator 1 if you want. So is every q-matroid induced by an Fq-linear rank metric code? I believe the answer is no, but we don't have an example yet. The examples get quite big quickly, or the cases rather. So, but that's also not the topic I want to talk about. Instead, let me turn to equivalent definitions of q-matroids. Now, just like in the classical case of matroids, there are many ways of defining a q-matroid. So I'm sticking to q-matroids at the moment, not polymatroids, so integer-valued rank functions. So, and I gave the definition based on the rank function, but one can define q-matroids based on various other objects, distinguished objects of a matroid. And that has been worked out in these papers there by Byrne, and Jurrius, and a bit of this was already earlier in Jurrius Pellikaan's paper from 2018. So equivalent definitions based on other objects of a q-matroid. This list looks actually identical to what can be done for classical matroids. One also has this bunch of equivalent definitions. But I would like to stress that these are really non-trivial Q analogs. It's not obvious how actually the axiom systems for each of these objects should look like, and then to prove that you get an equivalent definition of a Q-matroid. That is not at all trivial how to do that. But at any rate, that has been all fully established thanks to these papers here. So, question, can one do something similarly for polymatroids, for q-polymatroids? And the answer is yes, sort of, based on independent spaces. And that's what I'm going to show in the rest of the talk. How that works, what are the differences, and what the final answer then is. So, and this will also show that there are a lot of differences. And that's not surprising, these differences. It's also in the classical case, there is a big difference between matroids and polymatroids. Polymatroids don't behave so well. And the same happens in the Q-analog world. So I'm going to go and first show you the equivalent definition of Q-matroids based on independent spaces, and then try to generalize that, or try to see what we can salvage there for Q-polymatroids. So let's start first the other way around. We start with a q-matroid based on the rank function as I gave it in the beginning. What is an independent space? Well, we call a subspace independent if the rank value equals the dimension. So that's maximum possible rank value. These spaces are called independent. They have a lot of nice properties, which we will see in a moment. And I call curly I of M the collection of all independent spaces of this q-matroid. And then Jurrius and Pellikaan proved, her name is all over the place here in my talk. Okay, so they proved the following. And that gives us actually also this equivalent definition of q-matroids based on independent spaces. That's because there is an if and only if. So I packed everything into this theorem. Let's now try to unpack it here. So we start with a collection of subspaces, just any collection, curly I. And then to make the formulation a little simpler here, I introduce the following. Curly I of any V is the set of all subspaces in I contained in V. Okay, I of the putative independent spaces of the matroids, so I probably call them already independent. So I of V, the independent spaces inside V. B of V, the independent spaces inside V that are inclusion maximum. This is actually what they are called bases, but we don't need the name, but I'm going to use already the name bases without defining them better than this here. Okay, so this is just two notions here. So, and then given our collection of just spaces, then this collection forms the collection of independent spaces for a q-matroid M, if and only if it satisfies the following three properties. And the three properties are, it's not empty, closed undertaking subspaces, as you know from linear independence from linear algebra. And it also has the extension property, the second one here, which says that every independent space can be properly extended to a larger independent space by adding a non-zero vector, a suitable non-zero vector from a larger dimensional independent space, similar to linear algebra, if you want. These two, which are actually three properties, these three are kind of the analog of the classical case. The last one is really needed, which is the Q version, which is where life is so much harder. And it looks like follows: for any subspaces and any bases in these subspaces, there is a basis in the sum of the subspace that's contained in the sum of the bases. Okay, so once more, if a collection of subspaces satisfies these three properties, then it is the collection of independent subspaces in the sense of a q-matroid. What is the q-matroid? Well, we just have to define the rank function in this form. The rank of V is the maximum rank over all independent subspaces inside V, or all subspaces from I inside V. So first of all, we see the independent subspaces of a matroid satisfy these properties, and secondly, any collection with that property then gives us a q-matroid. So that is one form of a equivalent definition of q-matroids based on independent spaces. So now let's move to q-polymatroids. So again, the only difference is that the rank function now takes rational values. We first need a definition of what is an independent space. Here are two definitions. We came up with the second one, actually. The first one also appeared kind of at the same time in the literature. So a subspace is called strongly independent if the rank equals the dimension. Same as for q-matroids. And then in the second one is really tailored to q-polymatroids. Let's assume we have a denominator mu, then we call a subspace mu independent if for all subspaces of it, mu times the rank is at least the dimension for all subspaces in there. Okay, and this definition is actually taken from classical polymatroids, as one can find it, for instance, in the book by Oxley on matroid theory. So a few comments. First of all, strong independence is indeed stronger than mu independence and applies mu independence for every denominator. Strong independence is actually a very restrictive property. There exist many q-polymatroids where the only strongly independent space is the zero space. So, nonetheless, there are others where there are strongly independent spaces, and these spaces do in fact have a good use. They are used for the subspace design Relinde was talking about earlier. So, but for our purposes, characterizing Q or getting it at a definition of q-polymatroids, they are too restrictive. In particular, they do not determine the q-polymatroid, just for the reason of the previous item there. They are just too few. So the strongly independent spaces do not determine the q-matroid. So question, what about the mu-independent spaces? Do they determine the q-polymatroid? First, an example, just to give a brief idea of how q-polymatroids look like. Here are two q-polymatroids, same ground space, f2 to the fifth, and I give the rank function there. I just give how often each rank value is attained, sorted by dimension of the subspaces. So for instance, among the two-dimensional subspaces, the value 3/2 is attained 28 times, and so forth. And I give that for both. This is a full list. We see that the two matroids are not identical, or polymatroids, I should say, or equivalent in any way because of the different occurrences, number of occurrences here. So what else? By the way, both of these q-polymatroids arise from MRD codes. Now, what else we can observe is that all spaces are two independent. Two is obviously a denominator here. So, and they are two independent, that means simply 2 times the rank value is at least the dimension. That is true. So all the spaces are two independent. So since the two q-polymatroids are different, genuinely different, the two independent spaces do not determine the q-polymatroid. So they do not. That may contradict what I said earlier, but we have not yet taken the rank value into account. And here is a big difference to q-matroids. The rank value is not a function of the dimension, not for independent spaces. For q-matroids, the rank value for an independent space is simply the dimension, but here the rank value can take different values even for spaces of the same dimension. So what this tells us, certainly, if there is any hope that the independent spaces determine the q-polymatroid, we need to take the rank value into account. And here are now the good news, first without the rank value. I come to the rank value in a moment. So given our q-polymatroid, denominator mu, our collection of mu independent spaces, curly I, so depending on mu, and then it turns out this collection satisfies exactly the same properties as for q-matroids. That were these 3 items. No standard taking subspaces, extension property, and this particular basis property with the according definitions. Exactly the same. So the collection of independent spaces, mu independent spaces, satisfies exactly the same properties. This is just the collection of spaces. It doesn't say anything about the rank values. That's the next result, which is also good news. So the rank value of any subspace is exactly the maximum rank value of the independent subspaces inside that subspace, mu independent. It's the maximum rank value of the independent subspaces in there. And secondly, all bases in V, so the inclusion maximal independent subspaces in V, they all have the same rank value, and that rank value is the rank value of V. So this is kind of the nice result. The next one is a little bit clumsy here. I think I'm going to skip that. So this result here tells us the independent spaces, together with their rank values, fully determine and uniquely determine the q-polymatroid. We know what the rank value for any arbitrary space is. And that now can be turned into an equivalent definition of q-polymatroids based on independent spaces. I don't want to go through the details of this result. It says, in short, well, you have to throw in all the properties that we have seen based on your collection of independent spaces, satisfying the typical properties, your rank function. The rank values on it have to have the usual properties of a rank function and some other stuff. And then it defines the pair of the collection of spaces plus rank values on those spaces. That pair gives you a q-polymatroid with exactly I as the collection of independent spaces. But it gets a little bit clumsy, and one has to really put everything in there, otherwise something will break down. In particular, there is a certain closure property that one needs, which I find actually somewhat disappointing that one even needs that, but we have a counterexample to that. So let me summarize. The independent spaces, together with the rank values, uniquely determine the q-polymatroid. Can be turned into an equivalent definition, but that gets very technical to have everything in there. Final comment here. It is not possible to define q-polymatroids based on bases, dependent spaces, or circuits. Definitely not. And for each of these situations, we have results, 2 q-polymatroids, not equivalent, same set of bases with their rank values, or dependent spaces or circuits. That doesn't work. The only hope is that flats may give a rise to an equivalent definition, but we don't know what the axiom of flats for flats should be here. It's definitely not the one that works for q-matroids. So that is it. Thank you. Thank you for listening.